Hi everyone, I'm Matt. I'm with VEIC. They are the parent company that runs Efficiency Vermont. Efficiency Vermont is sort of a similar counterpart type of thing to Mass Saves. We run utility programs, efficiency programs for all the utilities in the state. I started off as a laborer on hard construction and heavy construction sites, moving wheelbarrows full of cement from here to there. Eventually became carpenter and a builder and owner of my own construction company, went to school, got a degree in architectural engineering, went back, worked as an energy auditor for the low-income weatherization program, started working with VEIC. I've been in and out of there a couple times on my second tour of duty there. I'm having a lot of fun as an energy consultant these days, because things are happening really fast now. There's lots of new information coming in. People are eager to hear what's the latest thing, and I enjoy researching it and letting people know what's going on. So hopefully we can do a little bit of that today. So here's our agenda for today. We're going to talk about what we have for options, for equipment options, how they perform, what the economics look like. We'll talk a little bit about integrated and dual fuel systems. So here's our stated goal. We're going to provide you guys with an understanding of what heat pumps are and how to condition new homes with them. With respect to cold climate heat pump, things keep getting better. On the right, we're showing some improvements in heating capacity. So in this case, the listed heating output capacity at 5 degrees Fahrenheit is 15% higher than the nominal capacity of the unit, right? So that's pretty cool. At 5 degrees, this system produces more heat than it says it produces, than it's rated for. So things are moving in the right direction. That's the good news. Let's talk about new construction. What's on the menu? We've got all these options to choose from. So I think of this as like, this is our menu when we're setting out to say what sort of system do we want to put in a particular building. Here's our options in terms of heat pumps. We're going to talk about all this stuff today. We'll go into a little bit more detail. So let's talk about indoor units. So we have an outdoor unit. We'll get to that in a minute, like our options there. But for indoor units, we've got here's the old standby, right? The ductless. How many people have one of these in their house or their office, or know somebody that does? I mean, we've all seen these, right? So we're all familiar with this stuff. They come in variable sizes. They're great for large open spaces. The concept is you get it up high on the wall, and it moves either heated or cooled air out across the room. So they work better in larger rooms where they have access. I say line of sight access, I think, is how we should think of these things. They're fast, they're easy to install. They don't require a big, remodel. They're pretty non-invasive in terms of installing them. Here's a floor mount unit. They look kind of like a traditional little space heater. These are good for smaller rooms, entryways. I see them installed here and there. They're not super popular yet, but I'm starting to see, them here and there. I think they can be problematic because furnishings get put in front of them, or they just don't have access to the airflow that the wall unit has. They'll get hung up in stuff that's down here and not be able to project out across the ceiling. In terms of projecting out across the ceiling, we got stuff like this. So this is the standard ceiling cassette. You can see it up here. It goes 4 different directions, multi-directional. The one down here, these are the newer style ones. They're singular or bidirectional. The valves turn one way or the other. Those are great for large open spaces because if the wall unit over here couldn't reach the other end of the room, you could put these intermittently down the ceiling. We've got compact ducted systems. They come in a couple of different categories. Let's talk about the first one, is the low static pressure category. So low static pressure, any duct design professionals in here, any engineers? That means basically you can't put too much ductwork on it. Every duct fitting and every grill and register and elbow and length of pipe that you put on that thing is going to increase the static pressure of the duct system. So these have very low static pressure requirements, so very small duct systems, which is not to say very small ducts. In fact, you would think that the bigger the duct, the less static pressure it's going to have. But the longer the duct, the more static pressure it's going to have. So what we're seeing is these things are great for like 2 adjacent rooms. It can go in a closet ceiling and hit this bedroom and that bedroom. These are really handy for putting in if we want to sometimes integrate with the ventilation system. We can pump an HRV into this little duct system and move some fresh air in along with this. I'll get into that stuff a little bit more later. Then we've got medium static pressure. So medium static pressure, I guess you can imagine, okay, well, they can handle a little more static pressure. Some of these are going up to like 0.36 inches of water column. Again, very quiet, small footprint. This is often referred to as slim duct technology, if you see that in the catalogs and so forth. You do have to provide access to these things. So I said, yeah, you can bury it in a closet, but don't sheetrock it all in, because no one's ever going to be able to clean it or access it or service it. It is still, it's got moving parts in it, right? Someday that fan bearing is going to go or something's going to happen to it, and we don't really want to. It's nice to have an access panel, that's what I'm saying. I see them sheetrocked in, and we have a little slot where somebody can change the filter. And that always bugs me, but anyways, pet peeve. These things are more like a centrally ducted air handler. You can see where the refrigerant line sets go in up here. You can put additional hydronic coils into them for other heating purposes, cooling purposes. They go multi-position, so that you can install them vertically or horizontally depending on what you have for a utility room. This can be plugged into an existing duct system in a home and push the air from the heat pump throughout the entire house. Pros and cons on the ducted mini splits. They're a better option in the multi-splits. I'll get into that a little bit more later. Filtration and ability to pair with ventilation. That stuff's really cool. So when we get into the multi-split heat pumps, which is like you have one outdoor unit serving 2 or 3 of those indoor wall units, or a mix and match. Well, I'll just show you the next slide. So we're mixing and matching in some of this. Here's a single zone. We've got a multi-zone in the middle showing like a high wall unit and a couple air handlers. And over here we've got a branch box or several branch boxes serving many different types of indoor units. This is all possible. It's all being done regularly. But I will say that as we start going into multi-zone systems, we tend to, this is our most efficient system, the single zone ductless mini split. And we tend to lose efficiency as we go. I'll talk more later in the program about what the efficiency numbers are and how to look for the performance and compare performance of different machines against each other. But you know, people go to this system. Let's see if I can figure out the pointer thing. This system here on the right, and these things, they go to these for comfort reasons. This thing is basically a space heater. It's a point source heating system. So this is going to put heat only in the room that it's in. And some of that heat might migrate upstairs or to an adjacent room. But for the most part, which room is going to be at set point temperature? The room that this thing is in. Sometimes these things, depending on which brand you have and which model you have, will go into defrost mode, right? So the outdoor unit goes into defrost mode, and this thing will move a little cold air back into the house. Defrost mode is it tends to run backwards to warm up the outdoor coil to take the ice off of it. And when that's happening, the air temperature at the indoor coil can drop. It can make people uncomfortable if they're in the vicinity. Some are better than others. They all have sort of different strategies that they use. It's a thing. So here's your multi-zone mix and match. You can put all these different indoor units on one outdoor unit. So an example of this might be single family residence. Downstairs layout is a big open layout, big open kitchen, dining room, living room area. It's all pretty modern to have the rooms wide open like that. So that might be served by this wall unit. And upstairs, we might put a compact ducted system here to serve the bedrooms. That gives them some AC and gives them some nice stuff up there. We might see one of these out in the entryway or the mudroom or something. And maybe there's a ceiling cassette in an office or a den or something like that. We see this and people, kind of go through the catalog and they go, oh, I want one of these and one of those and one of these and one of those. Not all of these things work on the hyperheat models or the super cold climate models. So the ones that are rated down to -15, -20 degrees, some of these systems aren't rated to work with those. That's getting better. So here's another concept, this the VRF, variable refrigerant flow. The appeal for this is zoning. So these are typically commercial systems. We're starting to see them now. I haven't seen one yet, but the industry is starting to see them now in like large high-end homes. I think, this old house did one with a VRF system in it. And, but the appeal is zoning. So the really cool thing about these is they have these branch boxes here. So we can bring our hot refrigerant out and take some of it and put it back in. We can do cooling and heating at the same time. So in fact, the ones with heat recovery can take the waste heat from the cooling process and use it to heat other rooms in the building. That might be really smart if your building has like a gym in it where there's a lot of need for cooling, and it has a massage room in it next door that it needs to be at a much higher temperature. We can integrate that way. So there's a number of options for indoor units that can be used with the VRF system. You got wall mount, ceiling mount, flush mount, but also compact duct and whole house high static pressure systems. So kind of the sky's the limit, right? We can do anything with these. They are very expensive systems. They're big systems, elaborate systems. The outdoor units have compact footprints, can handle longer line lengths, which allows greater flexibility in where do we put the outdoor unit with respect to the building. That can be an aesthetic consideration for a lot of people in the residential market. They see, well, here's the thing about heat pumps is you're going to see that compressor outside. That has to be in a place that has access to free open air. If you restrict that outside unit, putting a fence around it or a bush in front of it or something like that, you're going to reduce its ability to move outdoor air across its coil, which is how it performs and how it operates efficiently. So they need to be out there exposed, and people are like, well, I don't want to look at that thing. Well, you kind of have to, because it needs to be out there. There's been some creative stuff done with it. We see them put sometimes on porches and underneath decks and things like that, get them out of the way a little bit. I do recommend you get the outdoor units out of the drip line of the roof. I think that's a terrible thing to have, and sometimes people build little roofs over them, or you can buy little roofs that go over them. But typically, if you can put it on the gable end of the building, that's better than putting it under the eaves. I guess if you put the outdoor unit, many of them are wall mount. They have these little wall mount brackets, and you can put the outdoor unit on a wall mount bracket, and sometimes that creates a little vibration. And I've gone into homes where the noise from the outdoor unit is greater on the inside of the home than it is standing next to the outdoor unit outside. It transmits and vibrates through the wall. The wall becomes a big sounding board, especially older 2x4 homes. They rattle. We're talking about VRF, not about that, but I went on a little tangent about outdoor units. Anyway, the central controller is the sort of the brains of the thing, and that's where all the refrigeration gas goes through the central controller, and it goes out to the units that need it depending on what they're calling for and what temperature gases they have available. Pretty smart stuff. So VRF holds a promise of heating and cooling only the rooms that are occupied, right, which saves energy. So its ability to control the temperatures accounts for this amazing efficiency that's advertised on these units. But I wonder if we're putting these in like super high-end, 20,000 square foot homes, are those people interested in like not heating rooms in their house? I don't know. I don't live in one of those houses. But I assume that it's possible, and we could all do that. Here's some examples. So we talked about this a little bit. Unlike conventional systems, which have a single set point temp, VRF gives you the flexibility to create dedicated zones that allow for a precise temperature control based on the homeowners' preferences. And some homeowners would like to keep the gym cool while heating the adjacent living spaces. And with the heat recovery, which is an option on the VRF systems, you can use the waste heat from the cooling cycle to do heating in a room that needs it. So there's a lot of promise here. My hope is that some of this technology will get scaled down a little bit so it's more accessible to the residential market. We do see this commercially. So yeah, look at the boost on the COP from the heat recovery. That's substantial. So that's the real promise here. Typically in normal homes, we're heating or we're cooling. There isn't such a desire to do both at the same time. So let's talk about the dual fuel in new construction, and this is that central AC unit that I was talking about. So for all fuels, install a heat pump instead of a central AC. So it doesn't matter if you're on oil or propane or natural gas, this will give you the ability to heat with electricity for some portion of the winter. And I'll talk about it a little bit in the next couple of slides about when it makes sense and when it doesn't make sense to use one fuel or another. But again, they integrate with the building. We can put the ventilation air into the air mix. We can condition the air to have it just be the right temperature, the right humidity, the right amount of fresh air involved with it. Most of these systems come matched to the indoor coil. So if you're replacing an existing central AC system, you may also need to replace the indoor coil at the air handler in order for this thing to work properly. So here's economic balance point. What we mean here is that when does it make sense economically to run the heat pump versus run the furnace, right? And that's based, this tool here is available online. You can get it here. So you would put in like what fuel you have. You put in your primary system efficiency. So in this case, we're looking at natural gas at 80% efficient. The duct and system efficiency, I don't really know what they mean by that. There were no instructions on this tool, so I just left it in the middle. Here's our natural gas rate. Here's our electricity rate. There's two characterizations for the heat pump that you're putting in. One is for cold climate units and one is for all units. So we can't get that refined about it on this tool. I would like to see some refinements made to this tool, but anyways, you'll see in a minute. It's pretty close enough. If we look at the results here, so here's versus a home using heating oil. Heating oil price per gallon. So here we're like a little over $3 a gallon in this scenario. And electricity, I guess in this case, is like around 21 cents. So here, we're good to use this thing until about 9 degrees Fahrenheit. So use the heat pump until it's 9 degrees outside, and then use the furnace. With natural gas, it's a different scenario, right? So here's our price for natural gas, and here's our electricity price. If we're paying this much for natural gas, we can run this thing down to, what's this, around 5 degrees. And if we're paying this much for natural gas, around 1.6, 1.7 per therm, right, we want to switch over at like 35 degrees. So your fuel price makes a big difference in when is it economically feasible to run the heat pump and when do you want to run the furnace. I'd like to see some refinements in the tool, but this gets us in the ballpark. If your customer, or if it's for you, if you're bulk purchasing your fuel for the year, a lot of people get into a payment program and they say, I'm going to lock in at whatever price for the year. That's when you would go and you would look it up on the tool and you would reset your economic balance point So that's one thing you need to consider is the economics. The other thing you need to consider is the capacity, right? So does my heat pump have the capacity to heat my house? And yes, but that capacity changes depending on how much heat the house needs and how much heat the heat pump can produce. And that changes with the outdoor temperature. So to start this, we calculate the heating load of the house. We need to know the heating load on the house before we can figure this one out. So in this case, we figured out the heating load. It's a low load home, a new home, at about 17,000 BTUs per hour. So we plugged that on our little graph here. I'm sorry, at around 15,000 BTUs an hour. Here's our BTU an hour thing here. And what temperature is it outside when we have no heat load on the house? Well, here we picked 65, and we drew a line between them. Now, for our heat pumps, we can go to AHRI, or we can go to NEEP, or we can go to the manufacturer and look up the data tables, and we can find out like what are a couple of different capacities on a heat pump on a couple different temperatures. AHRI will always give you the heat pump max capacity at 17 and 47 degrees. Those are knowns. So you can go to AHRI, you can look it up, and you plot it on your little graph here, and you say, well, at 17 degrees, I'm able to do like 11,000 BTUs an hour with this heat pump. At 47 degrees, I can do like 18. So you plot those things out there and you run a line between them. Where those two lines intersect is where the house, when you get colder than this, the house no longer has the heat pump no longer has the capacity to heat the house. So that intersect point D is our capacity balance point. That's where the heat pump can't keep up with the heat load in the house anymore. And in this scenario, that was 25 degrees. But you can do this for any house and any heat pump and figure out like, okay, well, when do I need backup heat? Might be a handy exercise even if you're putting in a single zone ductless mini split in the living room and letting the furnace take care of the rest of the house. Because you could say, well, when do we turn the furnace on? Good to know. Here's the bottom line for centrally ducted heat pumps, but size of heat pumps for the home's design load whenever pairing with oil, propane, or electric resistance. So I guess what he's trying to say here is like, when we have expensive fuels, we want to really go aggressively at the heating load of the house with a heat pump. And this is based a little bit on what we just saw with the economic balance point and the capacity and stuff. When we're sizing heat pumps, we got to know that we have a machine that's, we'll get into this more. There's a whole thing about sizing and selecting heat pumps, but let me just give you a little background. A heat pump has reduced capacity and efficiency as it gets colder, right? So it has this rated capacity. So yeah, it's a 12 kBTU an hour heat pump, but when it's 0 degrees outside, how many BTUs an hour can that heat pump produce? And what efficiency is it producing that heat at? So it's a variable target, you know? So like our home also has a variable target. Our home is also like needing more heat the colder it gets. And the heat pump is able to produce less heat the colder it gets. So there's like this balance point, this cross line. And when we design for the coldest day of the year, which is the design heat load, when we design for that, we're putting in a heat pump that's big, right? And sometimes those heat pumps, especially with the multi-zones, don't modulate well at part load conditions. So when it's not 0 degrees out, when it's actually only 30 degrees out, which is really most of the winter, the thing is not working at its peak efficiency. So we got to figure out like, what are we designing for? What are we trying to do here? If we're trying to do a net zero house that uses all electric, then we have to go at that design heat load. If we're trying to balance with another system, then we say, when does it make sense to do the heat pump and when does it make sense to do something else? When we have dirty fuels, when we have climate change, when we have expensive fuels, we need to go after those aggressively and size for that design heat load. But do it with the right system that's not going to make you inefficient when you're at part load conditions. They'll get into that more at the other session on designing But I want to bring that up because that's going to affect our control strategy. It's going to affect the stuff that we pick, the things we select. And the fuel prices fluctuate, right? So economic balance point changes all the time. So I train a lot of heating contractors, and I tell them, like, teach your customer how to do this, right? And tell them the importance of doing this. Show them those two scenarios and say, see how different this is, this fuel price versus that fuel price? I think, you know, it gives people better control and some skin in the game. Here's another system that's coming out of Canada. I have a contractor who's like really interested in putting these in. He's done 4 or 5 of them now. It's an integrated system. So on the upper right is the furnace, and these guys are building natural gas furnaces as small as 15,000 BTUs an hour, modulating furnaces. They'll modulate down to like 5,000 BTUs an hour. They're pairing them with a nice cold climate heat pump. They have their own smart duct system, which is pretty cost effective and pretty easy to run. It uses like a 6 or an 8-inch round main trunk, and then these little branch ducts that go off into the rooms. And it has a smart control that you can set balance points and things on. So it's kind of doing all of this and creating its own backup. So I guess around where I live, it's really cold, and they say people are really concerned about backup heat. Well, okay, this thing only runs down to minus 18 degrees, and then it shuts off. What do I do when it's colder than minus 18 degrees? Well, first of all, build a really robust thermal enclosure, which is what they were talking about earlier today. The thermal enclosure is part of the mechanical system of the home. There's no way around that, right? So they interact together. The mechanical system needs to be designed for the enclosure, and the enclosure needs to be designed for the climate, right? So we're in a cold climate. We want cold climate enclosures. We want robust thermal enclosure. We want triple pane windows. We want R40 walls. We want all that good stuff. We want super airtight, good ventilation systems that don't blow a bunch of cold air around the house. All that can be combined with this. We're seeing these things go in, and the ventilation system being put right into this duct system, because this duct system is much smaller and more appropriately sized to put ventilation air into. Anyway, it's another option that's out there on the market for backup heat. So what do you do for backup heat? Well, if we're only needing a little bit of backup heat, this might be a viable option. We saw the environmental and the cost of using electric resistance heat. It's pretty extreme. We want to use as little electric resistance heat as possible, but it's maybe better than putting in an entire oil furnace just to do those 2 days a year where it's below minus 15, where a heat pump can't do it. So if we think about it in that way, okay, we're going to have 2 or 3 expensive days in the year, and the rest of the time we're working on our heat pump, and it's pretty good. I would say beware with this. There's people rush to this because it's inexpensive and it's easy. It's an easy, inexpensive solution to get that backup heat. And I monitor a lot of buildings. We have data monitoring systems in a lot of high performance homes, and boy, we know when they're running these things, and they do run them, and more than you would think. So let's talk about performance of these things. And if we're going to talk about performance, I'm sorry to do this to you, but we're going to have to learn some acronyms. So the first one would be the heating season performance factor, the HSPF. When you look up the data on a heat pump, right, this will be listed, the HSPF. That gives you a sense of how the performance of that thing over the course of a heating season. So like I said, when it's cold out, it's going to have reduced efficiency, and when it's warm out, it's going to have increased efficiency. But the temperature outside is doing this all winter long. So how'd you do at the end of the year? That's the heating season performance factor. Unfortunately, it's for climate zone 4, so it's not that applicable in northern Vermont where I live. In terms of, I can't take that number and plug it into equation and get good energy use calculations, predictions, but it's a great comparison tool. I use it for comparing one heat pump against the other. The SEER, seasonal energy efficiency ratio, kind of the same thing for cooling. How does it do for cooling at the end of a year It's going to be it's going to perform better when it's not that hot out at cooling, and it's going to perform worse when it's really hot and humid out. So how did you do at the end of the year? Seasonal. The EER is the energy efficiency ratio, and if you're like a utility or a utility program, this number is important to you. This is like, how does this thing perform at cooling when it's 95 degrees out? How efficient is it when it's really working hard? Because if you're in the business of providing rebates for heat pumps, you want to know what it's doing to your load curve. You want to do what it's doing to the grid. So if you have ones that are okay at part load conditions but not so good at full load conditions, that's going to increase your peak load on the grid. So that's an important number. COP, coefficient of performance, that's energy output divided by energy input. So that gives us a way to tell how efficient is this. So if I have a COP of 1, that's like what we get out of electric resistance heating. If I have a COP of 2, that means it's 200% efficient. COP of 3, 300% efficient. How do you get 300% efficient with heating? Well, we're not burning any fuel, we're not making heat, we're moving heat. So if it takes 1 unit of energy to move 1 unit of heat energy from outdoors to indoors, that's a COP of 1. If it takes 1 unit of energy to move 3 units of energy from outdoors to indoors, that's a COP of 3. And that's how we can get those. So it's a matter of input and output energy. And that gives us a way, that's more like, but that's a real-time number. That's not a seasonal number. The seasonal number is the HSPF. The COP is real-time. So we'll see COP listed at different temperatures, right? So what's the COP at 10 degrees outside and 70 degrees inside? What's the COP at 20 degrees outside and 65 degrees inside? Those numbers are in the manufacturer's data tables, and it's really important to look at those tables and understand what our COP is at different temps. So we'll get these energy guides. These are typically going to give us seasonal energy efficiency, SEER, seasonal energy efficiency ratio, and the HSPF down here. Heating fuel costs. So heating fuel comes in lots of different types, and they all have their own specific units, and each of those units has so many BTUs in it, right? So how do you compare, if I pay, $2.50 a gallon for propane, how do I compare that against paying $250 for a quart of wood? So we got to break them down into dollars per million BTU, which is what we've done in the end. This column over here on the end, you can see natural gas at $1.47 a therm. We're burning it at 90% efficiency. That costs us a little over $16 per million BTU. If we have straight up electric resistance heat, 22 cents a kilowatt hour, that's more like 64, almost $65 per million BTU. See the disparity there? Cordwood is right in there with natural gas. Of course, it depends on your wood stove and your natural gas combustion. Here's heat pumps down here at 23. And heat pumps and wood pellets are pretty close. Natural gas is going to beat it a little bit in this area. Where I live, we pay a little bit less for electricity and about the same for natural gas, a little more for natural gas, and it's kind of on par with natural gas. One of the cool things about these things coming up is they have a much better capacity to retain heat. So the heat doesn't drop off like it used to, the heat output with temperature. They're much better heat output at lower temperatures. Of course, that's a double-edged sword. We're paying for that with performance sometimes. Going after those cold temperatures reduces the ability to modulate and work properly in warm temperatures. So we're looking at efficiency or capacity. How do we get both, right? Well, NEEP helps us understand all this. NEEP has really stepped up in, to define what a cold climate heat pump should be able to do and give manufacturers a standardized way to show the performance of these heat pumps, right? You can go to the NEEP directory here. So here's what the tables look like when you look up your systems. Two different heat pumps. On the left is a 24 kBTU multi-zone ductless heat pump. On the right is an 18 kBTU compact ducted system. Highlighted in yellow is the minimum heating capacity at 47 degrees. And the multi-zone system can only modulate to about half its max capacity at this temp. So the compact ducted system modulates to a little under a third of its capacity at this temp. So how do you think a bedroom with a 6 kBTU indoor unit on this multi-zone is going to operate when it's 47 degrees out? A little room that thing can only turn down to 3,000 BTUs an hour. When it's 50 degrees out, do we need 3,000 BTUs an hour in that room? No. So what's a heat pump going to do? It's going to shut off. And then it's going to turn on, shut off, and turn on, shut off. But that's also going to be dependent on what's going on in the other rooms that have the airheads that are connected to that multi-zone system. So beware, this kind of stuff happens. And look at the COP differences between these results. I don't know if you guys can read these. COP here at 5 degrees, minimum output at 5 degrees, 4.45. Here, 2.29. Right, COP 5.52 at 47 degrees with minimum output, 47 degree minimum output, 3.59. So significantly better on the system on the right. And mostly because of its ability to modulate and run properly at warmer temperatures. So that's a multi-zone versus a compact ducted, right? So the reason I bring that up is look at this. Here are multi-zone and compact ducted systems installed in the same floor plan. Here we have the bedrooms, all have a duct in them. Here's a little tiny bedroom with one little tiny piece of outdoor wall on it. And that thing can only go down to 3,000 BTUs an hour, right? So that's not ideal for that situation. Also, we don't have anything in the bathroom rather. There's no heat source in the bathroom. So in a lot of cases, people would put an electric resistance heater in there. But we've got heating and cooling in all the bedrooms. Checked all the boxes, we're good to go. If we think about it through a little better, what might be a better option for this, just based on the performance specs that we saw in the NEAP catalog directory, here is a compact ducted unit in a little drop ceiling in the hallway. We got a quick duct going here, boom, boom, into these two rooms, a duct here, and then one into the bathroom. Central return in the hallway, bedroom doors undercut. That system's performing much better than this other one. And we got heat, we took that electric resistance heater out of the bathroom because now we've got ducted heat into the bathroom. Does that make sense to everyone? So what's the value? I did a study. We have a high performance home program at Efficiency Vermont. We built a number of, when the pilot year happened, we built a number of these homes. We put monitoring data in them. I went back and talked to those people like 2 or 3 years after they'd been living in their houses, and it's like, how's it going? How do you like your new high performance house? What's it like to live here? What was it like to build it? What was your experience like? And they all said, I'm amazed at the comfort. Right? The comfort is something I didn't expect. How comfortable. I knew I was going to be more comfortable than my old house, but I didn't understand the level of magnitude, how much more comfortable I would be. These non-energy benefits end up being a big deal. You know, in my world, we get pretty nerdy about the energy use and we forget about this stuff, but this is what sells houses. This is like what people are looking for when they want to buy a house. So I can't stress this one enough. Design a thermal enclosure as part of the system, integrated design. The mechanical systems and the thermal enclosure have to be working together. They have to be right-sized. Don't undersize or oversize your heat pumps. Don't cram the ducts into buildings as an afterthought because we never get good flow or velocity, or don't blow air directly on people. Don't put that thing facing the living room couch because people are going to be unhappy sitting on the living room couch now, right? Especially sedentary people. I think in a kitchen or a hallway, big deal, right? But if you're like sitting, end of the day, tired, you don't want that thing blowing on you. Even if it's blowing conditioned air at the right temperature, it's still uncomfortable to sit under it. Here's the economic benefits. So we have the initial cost and then the operating costs in the light green on the right. So here what we're seeing is ductless heat pumps, lower initial cost, lower operating cost, on par with a natural gas furnace. we can drive the operating costs way down if we have solar PV. But we're paying for solar PV instead of operating costs, so it's a little bit of a shell game. But seriously, what it does to the greenhouse gas emissions is awesome. So if for no other reason, consider this. On par in terms of cost, look at the environmental benefits, right? That's why we should be really considering the heat pumps with the renewables. There is maintenance on these things. I'm becoming aware of this. We've had heat pumps programs in place now for about 7, 8 years. And we're starting to see some really dirty heat pumps pop up. People are like, oh, my heat pump's not working anymore. Well, why not? Well, I don't know, it just isn't working. And somebody goes out there and says, it's packed full of junk. Nobody ever cleaned it. So there's more than just cleaning the filters, right? They got to go in every now and then, and there's a bag that they put around it and a sprayer. They take the housing off of it. They spray it, all the inside coil and the blower. They spray all that off. Yeah, so here we are. So we took the cover off it. We're spraying it out. Look at the water that's coming out of that thing. This is an eye-opener for me. I'm like, okay, we have a program for installing these things. Now we need a program for cleaning them. This is kind of worst case scenario. I'm shocking you with this, right? So this was, I'm really glad he was able to put that in there. This was an 8-year-old high performance home, passive house home that was built as a Habitat for Humanity home. The people who lived there are heavy smokers, and this is very near the kitchen. It's like maybe 15 feet away from the stove. So it's a small house, the kitchen's here, the dining room's here, the living room's here, the heat pump's here. They had pets, they're heavy smokers, they're greasy eaters. I'm not disparaging them, they're super nice. The guy was really gracious to us to let us in and do this, clean his heat pump for free. He was aware there was something wrong with it. Yeah, it just doesn't, I don't know, I'm not as comfortable as I used to be. He had no idea like what was up. But when he saw this, he was like cleaning out the ashtrays and like, okay, yeah, that's what's going on there. So this was 8 years of heavy use, no cleaning. But I would say even if we have a quarter of that in our heat pumps after 4 or 5 years of normal use and no cleaning, that's something we should look at, because that's the air in the room is moving across that coil all the time. So it's not like there's no maintenance. There is maintenance beyond just cleaning the filters. Outdoor units, same thing. We want to spray that out, clean that out. Don't take a brush to it. Don't maybe really have a professional come and do this. Costs, I think these guys have a new business that they're doing just heat pump cleaning, and they're costing like $150 per heat pump to do this, which every 3-4 years is probably a good idea. So here's the integration thing. Complementary technologies, meaning ventilation. Anybody have HRV, ERV in their home? Heat recovery, energy recovery? So a few hands, a couple. So in Vermont, we have an energy code, and the energy code says you need to at least have a bath fan on a timer for a ventilation system. I don't know if it's similar here, but that's what we're up against. And we kind of, you ever have a hunch where you're like, that can't be good enough. Like that doesn't seem right to me. So we went and tested CO2 in master bedrooms in 22 different houses. And these houses were existing homes with qualifying bath fan systems. So they were not tight houses. They measured anywhere from 2.5 to like 6 ACH 50. So not tight houses, normal houses. We did this thing where we put the monitor in the master bedroom, and we did one night with the door open, one night with the door closed, third night open, fourth night closed. Open, I guess we're in here somewhere, average part per million at around 1,000 parts per million. 1,000 parts per million should be the set point to trigger a ventilation event. That's when you know you need to put some fresh air in the room. That's with the door open. The door closed, we're seeing this. This guy spiked at over 5,400, which was where our meter kicked off. And a lot of them were in here 2,000, 3,000, couple fours, but you can see the spike. So cognitive effect of CO2 buildup, you feel groggy, you feel not right, kind of tired, cognitive effect, can't think so well. Yeah, and it's not just CO2s, it's VOCs and all kinds of other stuff that we're not measuring for because we just don't know about it yet. But if you just take CO2 and knowing what we know about CO2, let's make sure we get some fresh air into the bedrooms, right? So for at Efficiency Vermont in our residential new construction program now, it's required that you put in a qualifying high efficiency HRV or ERV system with ducted air to the bedrooms. Ducted air to all bedrooms and at least one fresh air duct to the main living space of the house. It's also recommended, not required by us, but it's a good idea to do dedicated stale air exhaust from the bathrooms and the kitchen, right? You want to put fresh air to where you are breathing, and you want to take stale air away from places that have bad air quality. So how do you do that? You do that with these things. So this is a little schematic of a HRV. So the way these work is they take fresh air from outdoors and they bring it in and they blow it into the house. And the stale air from indoors comes in and goes outside. As the stale air goes out, it gives off its heat at the heat exchanger core to the fresh air coming in. Now, the amount of heat recovery that we get is called the sensible recovery efficiency of these systems, SRE. And you can look that up. And again, the SRE changes as the flow rates change. So if we're running this system at 200 CFM, we're going to get one SRE. If we're running the system at 50 CFM, we're going to get a different SRE. And the 50 CFM is going to be a better heat recovery because we're moving those airstreams slower. They have more time to give off its heat to the incoming air. So it requires ductwork. This is the best thing we can do for air quality. The higher the sensible recovery efficiency, the warmer that air temp is going to be in the wintertime. So when it's cold outside and we have a higher recovery efficiency on the ventilation system, we're going to get more comfortable air moving through our house. It's not going to have the energy or the comfort effect of a low SRE system. Now, that being said, even a low SRE system is better than no system, knowing what we know about fresh air. But since we know what we know about these systems, let's put in the right ones. So we developed a qualified product list of ventilation systems, which in order to use those, we're looking at sensible recovery efficiency. We're looking at, does it have an ECM motor, electronically commutated electric motor to run the fans? There's fans in this thing. So that we can get the electric use down on them. And does it have a good cold weather defrost strategy? Imagine warm, moist air going out, cold, dry air coming in. We're going to get some condensation and some freeze ups in the core. So these things have to have a strategy to manage that. Here's a different kind of heat of ventilation systems that use heat pump technology. So these things have heat pumps in them. They're ventilators. They have heat pumps in them to condition the ventilation air, right? So we are using these things in some homes to provide a portion of the heat in the home. If we have a very low load home, maybe 10,000 BTUs an hour, like a passive house kind of thing, this might be able to do half the heat for that house. We can pair that with a really simple, small, compact ducted system and get all the heat for the house. So talk a little bit about the ventilation and the distribution. In this little floor plan here, we're showing a couple of wall-mounted ductless mini splits, supply air in the bedroom, supply air in the living room, return air in the bathroom, return air in the bathroom. So that would be a ducted system. You can pair them with the heating and cooling ducts, but there's an issue of size. So the HRV might be looking to move 150 CFM. The furnace might be looking to move 1300 CFM. So the ducts designed in the home are designed for the furnace, big ducts, big blower, big stuff. The ducts designed for the ventilation system are small ducts, small blower, small stuff. If you put the ventilation air into the space heating ducts, the fan isn't big enough to pressurize that duct system to move the air. So we need to turn the blower and the furnace on if we're going to do that. So we use the furnace blower to move the ventilation air around. So we have more of an electric penalty for doing that than we would if we were using a dedicated ducting system. But that being said, some of the furnace blowers now have ECM motors and variable speeds, and we can get that dialed in pretty nice. The cool thing about building a very energy efficient home is that we're bringing the loads down now low enough where the duct sizing that we need for heating and cooling are pretty similar to duct sizing that we need for ventilating. So now we're able to multitask with those duct systems. If we have R40 walls and triple pane windows, we don't necessarily need to put a duct register under every window, and we don't need to have baseboard hot water around the whole perimeter of the house, because we're doing that with our thermal enclosure instead of with our mechanical system. We're providing comfort in a different way. So the bottom line here is that the low load homes need ventilation. And I think I went a little further than that, is that all homes need ventilation. Low load homes especially need ventilation, but all homes need ventilation. So don't just pick on the low load houses. And maintenance is a big issue on ventilation systems. I just saw a study that went back to 10-year-old homes and found that a large percentage of them are no longer using the HRVs. Oh, that thing stopped working, yeah, a couple years ago, right? Oh yeah, that thing. Yeah, why don't we use that anymore? Sometimes a new owner came in and didn't understand the importance of using it. Sometimes something went wrong with it, the blower motor fritzed out, or the filters were plugged up and just nobody dealt with it. So maintenance, again, we talk about maintenance on heat pumps, maintenance on ventilation systems too. We're all pretty good at having the oil burner guy come every year, but we also need to consider like maintenance on these new systems that are replacing those old systems. There's no free ride here. Yeah, I mean, especially with ductless mini splits, I counsel people set it and forget it. So put that thermostat where you want it. You know that video I showed where we were cleaning that heat pump? That was a passive house, Habitat for Humanity house. We built 3 of those homes that were basically identical. And in one home, a family of Sudanese refugees moved in there, and there's like 6 people living in the house, and they turned their heat up to like 85 degrees, as high as it would go, and left it there all winter, the first winter. And we were shocked. We were like, oh my God. All right, well, they want to be warm. I mean, of course, be warm. And then the house next door, a thrifty family of 4 Vermonters, turned their heat down every night. They turned their heat down when they went to school. They turned their heat down, turned their heat down. They kept it at 64 when they were there, and they turned it to 54 when they left. They used more energy than the house next door, who kept their heat on 84 degrees. So it is important. The reason for this is, I'm just going to go to.
So the reason for that high use of energy is because everything in the house becomes radiator. So when you cool it down,
There's the cooling effect of every surfaces in the house.
walls, floor, ceiling, and then when you turn the thermostat back up, now you have to warm everything down.
That's part of it. The house cools down, the objects in the house, the walls in the house, the floors in the house, the furniture in the house, everything gets cold, and those things all need to be brought back up to temperature, because even if we bring the air temperature back up, they're sucking the heat back out of the air as fast as we can put it in. We got 5 minutes left. The other reason for that is that if this thing is sized properly, right, it has reduced efficiency and reduced capacity in cold temperatures. When we set the heat back at night and we want to lift that heat 10 degrees in that house, we don't really have the capacity to do that. When we had 100,000 BTU an hour gas furnace in there, you could turn that thing up and your house would be warm in 5 minutes, no problem. When we have a 15,000 BTU an hour heat pump in there, that's a different story. And it's struggling to do the work in cold temperatures. So it doesn't even have its 15 BTU capacity. So the combination of those two things is sort of like the the killer, the efficiency killer on that. The outdoor unit placement for snow, certainly not under a metal roof where it's going to get a slide and a big dump. Out of any known drifting areas, above snow lines. So they come on stands typically, and they'll be standing maybe 2 feet off the ground. We have snow. I'll give you an example. At my house, I found the perfect place to put my heat pump. I got it, 3 feet in the air off the ground, but I didn't realize, because I just bought the house, that when the conditions are just right, the wind dumps a huge drift of snow right there, and I've had to dig that thing out a couple of times. So important to know the local microenvironment in terms of drifting snow, but up above the snow line, out of the drip line of the roof. Under a roof is okay, because most of these things eject the air. They take it in from the back and the sides and eject it out the front. With the old air conditioning systems, the central AC systems, they would take it in the sides and push it out the top. So you couldn't put a roof over that. But now, with the mini split heat pumps where they push the air out the front, you can put a little roof over them. I do recommend you're going to do that just to keep the thing out of the weather. Also to keep splashback from hitting off the drip line of the roof. Splash is it's going to hit the heat pump and splash back onto the building, which can have a deterioration effect on the siding and the building. That's a great question. It's about the control, and I think when you can't, sometimes it's a temperature, like the heat pump can't keep up with the temperature in the building this comes on. For Mitsubishi, it's based on whether or not the heat pump can meet the set point control. If it can't get within 4 degrees of set point temperature for more than 20 minutes, this thing comes on. That's logic built into the heat pump. But controls is one of the cool. We're in the 21st century now. Controls are awesome, right? Sensors are getting cheaper and smarter. People are getting better at using them. I've seen some pretty amazing things done with controls. We are out of time now. Thank you so much.